Good morning and welcome back. So, I talked earlier about this notion of experiments to change your life for, and I guess we can broaden that category to include papers or books to change your life for. And this particular case study is really, truly one of my favorites. It's something I learned about kind of in succession, started to learn about island biogeography. That led me to The Song of the Dodo by David Quammen, who I think is one of the greatest of current day science writers. And I have to say, as a little plug, that I think that practicing scientists have tons to learn from professional science writers. And the reason I say that is that they are quite scholarly and they can provide you an entry into very rich literatures. And so Quammen had this really quite amazing book that led me in turn to several others where I learned about oceanic dispersal. And so this case study is part of our ongoing series of the physics of migration, herding, and dispersal. And this will be, I think, the defining example of this notion of dispersal. So we begin with a puzzle, and the puzzle concerns the island of Sao Tome in the Gulf of Guinea. You can see that's the west coast of Africa above and on the right. And what's interesting about this particular island is that it harbors 7 species of amphibian. And when I use the word oceanic island, you see on the bottom the profile of the islands themselves. And what I want to illustrate is that the islands, the ones that we're talking about, are oceanic in the sense that they've been always isolated. It's not like New Zealand, which broke off from a previous supercontinent. These islands are volcanic usually, and they appear forthwith in the ocean. So why is this a puzzling observation? And the simplest thing I can say is, these are several experiments or measurements that have been done that basically address the question of dispersal of amphibians in the ocean and effectively treats of the question of how these animals respond to being immersed in salt water. And so, for example, on the top right, you see a survival curve, percentage survival as a function of time. And you can see that after 24 hours, the number of survivors is around 30%, and it continues to get worse after that. And, we'll come back to the question of how long it might have taken, for example, for a frog to raft to the islands in question. So I already commented on the notion of oceanic islands, and I show you here a number of very, very important biogeographical examples that should cause all of us to stop and think about how to use the words of Darwin, how the islands of the world were peopled. And the upper left shows you the Hawaiian island chain. The upper right shows you the Galapagos, with to the west the the newest islands, Fernandina and Isabella. The lower right is the islands in question in the Gulf of Guinea, and then the lower left shows you the one with cloud cover kind of in the center is Bali, and then to the right of that is Lombok, and the channel that separates them, the Straits of Lombok, was part of what amounts to a boundary that was articulated by Alfred Russel Wallace for what we now call the Wallace Line, because he noticed that the flora and fauna to the east of Bali across what is now the Wallace Line was very different, involving birds of paradise and marsupials and stuff like that. So anyway, that's what oceanic islands are. And I think, when we look at the map, you can see here the west coast of Africa and the disposition of Principe and Sao Tome in the Gulf of Guinea. So I already mentioned the fact that these are oceanic islands, and now what I want to do is I want to give you a little bit of a record of sea levels over the last, say, 150,000 years. And the 0 point is the current depth, which you see at the left. And then as we move to the right, we're moving back in time. And the thing that I want to call your attention to here is I'm about to give you a sense of the depth of water in the Straits of Lombok and in the vicinity of Southeast Asia over the last, say, 20,000 years. So this is the Sunda Shelf. If you ever fly, for example, from Singapore, which is sort of up in the middle left, about where the 0 is, maybe you can see my mouse. But there's this is Singapore over here, and down over at the 115 on the x-axis and up about -9 is Bali. If you fly from Singapore to Bali, you'll fly across the Sunda Shelf. And what I want you to notice is that, at this time, the water level was very different than it is now. So, what we're going to watch is the penetration of water over, you can see in the upper right, the timing. So this is 12,000 years ago, and, something like this. And, these are interesting time scales because this is relevant also for what was going on here in Los Angeles, where this course is taking place at Caltech. We have this famous fossil site, which is the La Brea tar pits, and the time scale of interest there is, say, the last 60 or 80,000 years. So, I keep advancing this, and one of the things you would have noticed down, if you look at Bali and Lombok, is that they always were dark blue between those two islands. So, going off to the east, as I already remarked, the flora and fauna of Bali were isolated and separate. Whereas, if we go back in time, you can see very clearly that Bali and Java were connected. Okay, so this was just to comment on the notion of oceanic island, and to come back to the situation with the amphibian species on the islands of the Gulf of Guinea. These islands have always been separate from the mainland of Africa. So that's part one to the puzzle. So I already commented on the fact that there are oddball species, and you can see that Principe and Sao Tome have variety of amphibian species, and we're going to focus on one of them, which is this particular species, a frog, and I show you the size down at the bottom. Now, the reason I guess I got intrigued by this case study is revealed more by DNA science, and I wanted to, by examining the DNA of this organism and how it relates to other organisms on the mainland of Africa. Because just as we would think in the context of the Galapagos, you would imagine that the organisms that live on the Galapagos are going to be most closely related to the organisms on the west coast of South America or Central America. That's at least, let's say, we would formulate that hypothesis. So similarly here, we would be inclined to think that this frog is most closely related to the frogs of West Africa, and that is what DNA science has taken a look at. So I wanted to just give a little bit of a side note on the nature of technology and how it transforms our ability to ask questions about the world around us, and specifically for the purposes of this course, how it permits us to ask questions about the living world. So in 1609, Galileo turned his famed tube to the heavens, and in 45 days or so, he completely changed the face of science forever. And one of the main discoveries is shown here on the right. This is from his short book, The Starry Messenger, where what he noted was that there are celestial objects that orbit Jupiter. So there were 4 moons that he observed, and night after night he would look at their positions, which you can do also. And what he found was that these 4 objects were moving around Jupiter, and this, in a certain sense, is the death knell for the geocentric perspective on the nature of the solar system or the universe, or however you want to think about it. Because, clearly these objects are not going around the Earth. He also discovered phases of Venus, which is really most consistent with a planet which is traveling around the sun, and sunspots and imperfections on the moon and so on. And again, it really was the end of the line. But my point actually is, in some sense, about the subsequent history of astronomy and astrophysics, because in the 1800s, we saw the rise of spectroscopy, and I'm very, very interested in the rise of spectroscopy because it's an example of the requirement for patience in science. It was the early 1800s that people like Fraunhofer, started to discover spectral lines and trying to understand their nature. It was in the middle, sort of after 1850s, that people like Balmer were able to articulate a mathematical empirical relationship between the wavelengths in spectral lines. And it took until the mid 1920s before one could say we solidly had a handle on the nature of radiation given off by atoms in the periodic table. Well, this spectroscopy business was important because it was an add on, if you like, to the technology of the telescope that completely changed our ability to examine and think about the heavens. And it gives rise to a very important story. I would urge every single one of you, if you have a little time, and I would make the time, to read about Cecilia Payne-Gaposchkin, one of my heroes. She was the first person to get a PhD in astronomy at Harvard, if I'm not mistaken. She was the first woman to be tenured as a professor at Harvard, and what she did is she used this great database, and I think should be inspiring for biology. Careful measurements on the part of spectroscopists in the context of astronomy on cataloging the spectral character of different stars, and from that she was able to learn something about the composition of the stars, which completely turned on its head the prevailing thinking on the composition of the universe. So what's the story here? This is from Nature magazine in 1902. It's an article about the laboratory in Heidelberg. And so what I want to do is just read it to you. Its small beginnings in the middle of the last century are marked by the name of Kirchhoff scratched on the window of what is now the private room of the senior assistant. From this window, one may look out over the Rhine plain towards busy Mannheim, as Bunsen and Kirchhoff did one night when a fire was raging there, and they are able, by spectroscopic examination of the flames, to ascertain that barium and strontium were present in the burning mass. So what I want you to note here is the claim is that they could take chemical fingerprints in the form of spectral lines and identify what was in the burning mass in a fire, say 10 or so kilometers away. But the same window also looks across the Neckar to the Heiligenberg, along the slopes of which run the Philosopher's Walk, the chief of the many paths among the wooded hills around the town, which the two friends were wont to traverse in their daily constitutionals. And again, editorializing, this is a very easy thing for you to do. If you go to Heidelberg, which I think you should, then you can, right by the cathedral, have a nice meal, walk 100 meters, you'll be at the river, you can cross it, and right there you will find a sign that says Philosopher's Way, and just mount it and climb up the hillside, and it'll take you 45 minutes or something, and very weird and interesting things to see up there, which I'll leave as a surprise for you. You can look back down on Heidelberg. I think it's very nice that Kirchhoff and Bunsen took walks here. Bunsen is known to have said that it was during such walks that his best ideas came to him. One day the thought occurred, if we could determine the nature of the substance burning at Mannheim, why should we not do the same with regard to the sun? But people would say we must have gone mad to dream of such a thing. All the world knows now what the result was, but it must have been a great moment when Kirchhoff could say, Bunsen, I have gone mad, and Bunsen, grasping what it all meant, replied, so have I, Kirchhoff. So, what they did is to basically unite spectroscopes with telescopes, and, in a way, this is one of those classic, and the rest is history. For all of you students at Caltech, that means that you fly here often. That means that you will have the chance, if you fly in a flight coming from the east, and often whether you're coming from the east or west, you'll have the same flight path. And what I want to say is, I encourage you to get a right-hand window seat, because when you do, you will see Mount Wilson, which you can also see from campus. It's the antennas that you see as you look up to the north from campus. Those antennas are at Mount Wilson, which is where the Hooker telescope is. I think it's a 100-inch telescope that was used by Edwin Hubble with a spectroscope to measure redshifts, from which the Hubble law followed. So, starlight gives the history of the world and how the world works. Well, so too does DNA sequencing. So, this is a Caltech paper by Emil Zuckerkandl and Linus Pauling. I love the title, Molecules as Documents of Evolutionary History. And the comment that they make is shown on the left. In macromolecules of these types, there is more history in the making and more history preserved than at any other single level of biological integration. It's a great story. It's one I'd like to tell you, because genomics in the absence of genomes, it was a rock-solid subject that involved people like Pauling who used shifts on gels to compare the hemoglobins of different organisms. That involves Alan Wilson at UC Berkeley, who with Vincent Sarich did these beautiful analyses of the primate line by looking at albumin and how well antibodies bound to it depending on what species was the source of that albumin. This is off the top of my head, and I might be misremembering a little bit, but the key point is genomics, getting at the genome. And I personally love indirect science. I love science that does not require looking at the thing you claim to be thinking about, but finding some clever and bizarre way to look at it. And that, to me, looking at hemoglobin sequence effectively by looking at shifts on gels, and similarly looking at albumin are great examples of molecules as documents of evolutionary history. So all that having been said, the big claim here is that the frogs of Sao Tome are most closely related to those of East Africa. Let me just stop for a moment and let you digest that. The frogs of Sao Tome are most closely related, if you look at this phylogenetic tree, to the frogs, for example, in Egypt and Kenya and Uganda and Tanzania. That's on the opposite side of Africa. What they did in this experiment was to use the mitochondrial 16S rRNA gene as a window onto evolutionary relatedness. And I just want to point out that, as you see in the upper left, Darwin had this notion of I think, which is where he posited the life history, which is maybe better shown on the lower graph, which is essentially the same thing. So time is moving up, and what you see is the descendants with modification of evolution, and those particular fingers that stop, or branches, that corresponds to an extinction event. So these diagrams show the history of divergence and evolutionary change leading from a single ancestral lineage to a suite of descendants. So when I show you this for the frogs, what we're doing is we go to the left is we're going backwards in time, and if you like, the vertices correspond to a common ancestry. So I found this, an amazing puzzle, something that the whole story, amphibians on oceanic islands, already great, but then the plot thickens in a way because they're evolutionarily most related to the frogs of East Africa. I want to just say a little bit more about deep time and the ribosome. So this is a picture of Carl Woese, who, in masterful long series of works beginning in the 1960s, decided to use the ribosome because it's a shared thing. This is part of the unity of the living world, is everybody has ribosomes. And so what he did is, I'll remind you that the ribosome is 2/3 by mass RNA, 1/3 by mass protein. I think maybe I have a diagram about it. And so there's two large subunits made up of rRNA, and then what Woese wanted to do, by the way, here I show you that there's an interesting secondary structure. Certain parts are conserved, certain parts are less conserved, and so you can compare the ribosomes of different organisms as a window onto their evolutionary relatedness. And so that is the DNA that was used for this comparison. You could nowadays do it in a whole genome sense, but there, you look at a very, very small fragment of the entire genome as a window onto the evolutionary process. So, you can go look this up, which I did, and that's the outcome is this particular partial sequence from the mitochondria, and it leads to this very, very interesting conclusion. So that's my jumping off point for what will now turn into the physics.